There we go. Yeah, so I'm thinking maybe I was a little bit tired and that might have made me an extra cold, but it was freezing in here. It was ridiculous. And I have a lot of extra like blubber. I tried to come up with a better way of saying it, but there just really isn't. Works for whales, should work for me, is the idea. All right, let's share the screen here. And then let's look at our read function, or write function, sorry. All right, everybody online, I am recording. Everybody online can hear and see my screen.
Yep.
Okay. So just as a quick reminder from last class, we were talking about this idea of separated memory between user space and kernel space, and how the addresses are not, they don't map directly to each other. So we need to have a mechanism for crossing between the two layers. And one of those mechanisms, so here is kind of the problem, is you can use a memcopy function or just write directly to memory to write something to a memory address. The issue is that if you're doing this, if you're trying to write to user space from kernel space using memcopy, it won't work. Well, it'll work, but your destination won't be what you thought it should have been. Actually, modernly, it probably wouldn't work. I think you'd probably get an access error. But historically, you just didn't know where it ended up. And vice versa is also true. So we looked at from user access.h, we're actually using the one from Linux instead of the ASM, which is for the assembler. We are looking at these system calls for copying to the user and from the user. This allows us to translate between kernel space and user space. All right, and then last class we looked at the read function initially. Well, we kind of walked through this. There's our init module. All right, we talked about device opening, and this was kind of our ghetto semaphore. I kind of foreshadowed this idea of semaphores for inter-process communication, and this guy is not happening atomically, but we're trying to keep track of the number of people who have this guy open. Once it's open, we can then read from it. We're going to keep track of the number of bytes that we read. We, as long as our message pointer points to someplace real, we are asked to read some length. And this is how we're going to read. We're going to count down our length, starting at our base place in memory, and we're going to put to the user a single character through this buffer. And then we'll increment our message pointer, which will walk us one character down the string, and we'll increment our buffer, which will keep track to where we're going to put that inside the buffer. We'll decrement our length, number of things that we have left to read in, and then ultimately read our bytes. Now notice that what we're doing differently here than what we did before is before we would have done like an sprintf. We would have printed something to a string. The reason why we can't do that here is printing it to a string that was passed to us, for instance, this buffer, doesn't map directly if we are in the proc file system running on kernel mode and talking to a program that's in the user file system. So we can't directly write to that string. We have to indirectly go through put user to get something, get a value to that user. Make sense? All right, so that's our read, and then ultimately return the number of bytes that we read in. Oh, hold on a second. This isn't most of the example is still the same, but that isn't the one we were looking at. We're looking at Proc FS with write. And this is the one that has the space, yeah. Sorry about that. Most of it will be similar. Okay, same thing I said before, but notice here we are creating a local variable called buffer whose pointer we do have access to. We're printing the string to that guy, right? Again, this isn't a problem. sprintf is okay to print a local variable because we're living in kernel space in this case. But once we're done, then we're copying to the user that buffer. So this is where we're bridging between the two, ultimately returning the length. So it does something similar, but does it indirectly in this case. Now, writing to this file in the proc file system is, so we take in the name of the file we're writing to, the string we're writing. This is coming from the user space. How big it is, count, and then any offset. We're giving ourselves a local buffer here. I think buff size is what, 100 on the top, yeah. So as long as the offset is greater than 0, means we're starting at well, if it's greater than 0, meaning that it's something that is not on our string. So ppos would be, think about this, if this is an offset, all right, so this says if that struct has an address. This isn't talking about the value that's in it. Ppos is a struct of type offset. So this says if ppos has a value, we're okay. Or if count is greater than buffer size. So this if statement says return that we had a problem if ppos does not have a value or count is too big. So that's just some error checking. Otherwise, we will try to copy from the user, because remember, this is our write function. We're going to copy something from the user. What are we copying? We are copying from the user buffer that was passed in into our buffer, this local variable, using this count. That's the number of bytes we're going to read in. Where our local buffer presumably lives in kernel space. This guy's going to have a real address, a memory address in kernel space. So this is basically saying, right from this user space memory address into this kernel space memory address, this number of bytes. That's what that function ultimately says. All right. If something went wrong, return that something went wrong. All right. Otherwise, we're going to, I talked last time about the scanf function is kind of like Java's scanner. So we can read something in from the user. All right, so this is reading something in from a string. What are we reading in? Well, we're reading in from our buffer, which is this guy, that presumably we just copied from the user buffer into our buffer. So this guy now should have a value, okay? And it should look like this, 2 numbers. Okay, this is kind of an interesting thing how scanf works. Well, not just scanf, even scanf. So if I want to read something in from the user, I can read in more than one value at once. So this is saying I'm expecting 2 numbers, 2 decimal values. That's what it's going to read in. It's going to read in the next 2 decimal values from the user. And I'm reading them into this variable I and this variable M, where I and M are just 2 ints. So we're going to read in 1 decimal from our buffer, and I'm going to store that first one at the address of I. So that variable I will equal the value found in our buffer, the first value found in our buffer. The second thing here will be the second value. Now, why do you think these are %Ds when we're reading in from a string? What are we accomplishing here? I'm going to show you an example of maybe our string looks like this, 123 and 2. That might be an example of what buff equals right now. So buff might equal that after copy from user. So if buff looks like this, and I'm scanning in from a string buff 2 decimals, and I'm passing it the memory address of the 2 destinations. I want the first decimal to go here, the second decimal to go here. And I'm specifically doing this from a string. Why are we using scanf here, and why are we using %D here? What's ultimately the thing that's automatically happening for us here?
Converting to an int.
Converting it to an int. So scanf, string scanf, has the ability to say, you're expecting a decimal, right? Now, scanf is always reading from a string. So this first element here is always going to be a string. So you pass me a string, and then you tell me, how is that string tokenized? How do you want me to get the values? How many of them are there? And how do you want me to read them in? So in this case, it'll read in the first int it finds as a decimal, storing it at address of I. It'll read in the second decimal it finds as a decimal, storing that at the address of M. Good. Let's see. I think the answer is yes, because it will look for the second integer. If you pass it 3 integers, it won't break. It'll just grab the first 2. It's a good question, though. What if it's looking for... I'm kind of making a guess on how I write it. So if I were writing scanf and the user passed me 1 integer, passed me a single value, and I was expecting 2, what would I do? Would I leave the memory address, the thing at M, would I just leave that as the default value and not scream? Or would I crash? I think I think it'll work. I won't crash. And I think part of my rationale for that is more of a reading code thing. We're doing a lot of error checking here. And notice here at the end, it's asking if num is not equal to 2, something bad happened. So scanf must return for us the number of things it was able to read in. So if it only read in 1 thing, it's tough cookies. You didn't get enough information. If it read in 6 things, well, that's a problem too. But this should limit it from reading in more than 2 things. So this is saying, die off if you didn't get exactly 2 things. Otherwise, we're going to set our local variable IRQ. Well, it's a static variable IRQ. So it persists as long as this program keeps running. We'll set our IRQ and our mode equal to I and M that we just scanned in from that string. And then we will get the length of our string buff, which is the total length of what we read in from the user. And then ultimately, we'll keep track of the offset will be equal to C. How far off of that base address did we just read in? And notice that this guy is being passed in as the address of that offset. So this allows us to write that back. But again, this is going to be happening in kernel space. So this isn't a value that's going to be sent to the user. It's going to exist in kernel space to whoever called our myWrite function, which would be the proc file system's response to the user trying to write to it. Right? User tries to send something to the proc file system. The proc file system then says, okay, I'm a module. I existed because somebody created this node in the proc file system. Somebody's trying to write to me. What do I do? Well, they told me at the beginning when I was first installed, I call the myWrite function. And I'm going to pass it the stuff I just received. And we're trying to get that stuff over to a program running in kernel space. Make sense? Okay. So that's what's happening there. And I think, if I kind of remember at the end of class, I was trying to run it for you real quick, and there is a way to get, I was trying to echo to it. It said not allowed to or something like that. Let me just run it real quick again. There is a way to accomplish it, but it's kind of unimportant for us right now, because this next thing we're going to look at is what if we actually wrote a user program to talk to it. All right, so we'll go ahead and just do a make. Oh, I guess was I trying to run it from the command line last time? See, I had previously figured it out. I told you I had figured it out and forgot I had written it into a write function. So, you know, what we tried to do last time is, so if I do a tail, oh, D message pipe to tail 1671. Oh, did I need to install my module. Sudo insmod proc write ko. Here's our hello. That's our, once it was installed, I think we just printed out hello. If I read from it, notice it's giving me an IRQ of 20 and a mode of 1. This is just what it's outputting. Those are the static integers that belong to the kernel mode program. Those are the default values. All right. So now if I want to write to it, the idea of our write in this case is to update those static values, right? It's allowing the user to let this kernel space program know that I want IRQ and mode to change. Why we want to do that, who knows, who cares? But it allows us to do that. So if I do a more on write, just to show you, the command to do that is this echo. So I started off, let me just show it to you first. So I said echo, and I'll do 33 and 7. Redirect that to /proc/mydev. All right, we got this error last time that says permission denied. Okay, you gave me a string that I was trying to read in, but you're not allowed to write to that proc file system. So I said, oh, well, maybe I want to sudo it. Still permission denied. Then I did this thing with these little backticks. And the backticks say, execute what is inside of that. Boil it down to a value. And then finally, I could say I want to execute it using the bash shell. C. So this guy says, as super user, call upon the bash shell, passing it, I don't know what the -c is for. Let's do man dash Commands are read from the first non-option argument. So it tells you where to read in the command string from. So I'm feeding bash this command string. So bash -c, what's my command string? It's going to be echo. Actually, I can write it as a string now. Echo 33.7. And I'm redirecting to /proc mydev. So that's the string I want to execute. And there's me writing that 30. I think it spit something back out. Now, if I read again, there we go. So I didn't write it right even the first time. So I'm echoing a 33 and a 70, a 33 and a 7, and I'm just going to steal this so I can go and change it. So I'll change this to a 41 and a 2, or 41 and a 1, that's fine. So now I'm writing to my proc file. And then when I read from it, I should now see the 41 and the 1. So this is proof that I took something from user space. This was my 41. I sent that in from user space. It came in as a buffer to the write function, which I then copied into kernel space. And then I read from that. That was the scanf. Here's my write. So the first thing I did is I copied from the user that user's buffer, which was that string 41.1, whatever I put in there, and I copied into this local variable buff. Then I read in from that string the two pieces of information I was representing, an IRQ and a mode. And I stored this, the scanf, just like we've seen before, he returns the number of elements read in. But he stores those elements in these values. So if I had 5 placeholders, I would have 5 comma delimited values here. Starting to see the pattern in C. This is a pretty common pattern. Function returns the number of things that happened. The function itself passes in addresses where something should be written. It gives you the buffer. It gives you, in this case, I'm reading in this integer, and I'm putting that integer at this memory location. I'm putting that integer at this memory location. Make sense? Where I and M already are reserved places in memory. But to get the place where they equal, how come I'm not saying star I here? Why am I saying the address of I? What kind of variable is I? Cat, dog, or int? It's an int. All right, so are ints passed by value or passed by address? By value. So that means I itself is a bucket for holding a value, correct? And the value it holds is an int, not a pointer. So I can't say put a value at the place that I points to. Instead, I have to say put the first decimal you read in at the location where I lives, because I is a value, not a pointer to a value. That makes sense? That's why I'm passing in the ampersand I. I'm saying this guy is the actual memory address of I. This is where I lives in memory. So when I go and try to use the value of I, I'm going to resolve that variable. And the first thing I'm going to do is I'm going to find out where in memory is I. I'm going to go there. I'm going to get that value. So here I'm saying read this first value in and put it in this place in memory. All right, that makes some sense? All right, so that's why we're passing in that. If I was reading in a string, for example, that would be a %s. I would put in a pointer to a character array, because I don't want to store it, that character array, its value is a pointer, and following that pointer is actually where I want to store my string. Make sense? So this is saying, this first thing here, where are you going to put it? I'm going to put it in this memory location. So you feed it the memory location where you want that value to live. If it was a string, the memory location would be the address where a pointer points. That's where I would end up putting it, which is why I would say something like star buff. I could say %s, or then here would be star buff, like that. Star buff is the value that lives inside of buff, which is a memory address. So I'll write this string to that memory address. Make sense? All right. So read in the string, copied it from the user into kernel space, read from that string in kernel space, the two values out of it, set the static things that are owned by this module equal to that. So when I write, I am changing the value. When I read, that value is now changed. All right, makes some sense? All right, so now we've seen the mechanical way of writing from user space to kernel space and reading from kernel space into user space. Now, previously though, we couldn't read stuff like this. How were we able to see the output of our module? By looking at the message queue, right? So now we've decided, you know what, I no longer have to go and search this, I do a tail on this queue. Now, you know what, my module can give me responses because they can now get its stuff over to my side of the world. All right, kind of understand the deal going on here? All right, so now let's look at, we're probably not going to interface with our programs like this. Proof of concept that we can. More than likely, since we've been talking about inter-process communication, more than likely we're going to have another program, our process, that's going to want to talk to this dude. So let's go and look at that. Here's our user space test. Okay. So this is something that's gonna, this is just a user application, right? It's gonna run command line, whatever. We create a local variable for our buffer. It's just a string. We're gonna go ahead and open a file for reading and writing. Okay, so I'm creating a file descriptor. So this would be like the social security number of a file. All right, so file descriptors are ultimately ints. I think you'll find, well, we already know, we've heard the theme over and over and over again during our years here in computer science, is that computers like numbers. How they represent those numbers could be in binary, could be in decimal, could be in hexadecimal, could be in octal. Well, really, the decimal is the human side. That binary, octal, hex thing is going to be the computer side, but at the end of the day, it's always binary. But punchline is they like numbers. And since they like numbers, when we have this system call that attempts to open a file, what file? This file. What do you want to open it for? I want to open it for reading and writing. And what kind of animal is this guy probably based on what we've talked about in class? It probably is an integer. Okay, so that wasn't what I was fishing for. It starts with an M. Its value is probably an integer. What I'm asking for is, based on you visually seeing this thing written in all caps like this, what kind of animal likely is this?
A macro.
Yeah, it's a macro. Okay, so I don't know that 100% for certain. Now I do. Apparently this guy hovers over it. So notice it's a define. There's my macro value, read write, and it's equal to a 2. All right. So you're right, it is an integer, holds an integer. It's a macro. Now, what's the difference between a macro and an integer? Why do we use macros instead of integers?
It's reserved. It's like it's a pre-reserved number. It makes things more efficient, memory allocations easier, things like that.
Okay, it seems like you're saying a lot of things and you might know what you're talking about. So tell me more about that. What do you mean by reserved?
It's predetermined. So I remember you kind of talking about it before, where it's predetermined, so it doesn't like happen before compile time. So it's already in there, and then it just kind of makes things more efficient.
Okay, tell me about the efficiency side of it. So macro versus int, or any variable for that matter. So a variable is assigned actual memory in user or kernel space, in either user or kernel space where the program is running, because its value can potentially change. A macro is just a label that prior to compile a pass is made on the source files to replace all occurrences of that macro with its literal value. So we're not actually utilizing memory to store that value. Instead, we're holding the value that should be associated with this macro in one place so that we can easily change it. But when we go to compile, any use of that macro throughout the code gets replaced with that hard-coded value, not a variable. Okay, so that's where it is more efficient from a memory perspective. Probably not that big of a deal today, but the number 2 already exists. So why do we need to store 2 in a new place in memory when we can just have a way of, so a macro is almost like using a variable without having memory, but it's a read-only variable. You could think of it like that, and it doesn't come with memory. Think of this like a read-only variable. All right, so we're going to open this file, our proc mydev, for reading and writing, because we're going to be testing both reading and writing. We're going to read from it, we're going to write to it. All right, so now we'll go ahead and we're going to try to read from that file descriptor. So we've opened that file. We're going to read from it into our buffer, into our string, and we're going to read up to 100 bytes. Now remember, read is probably going to return the number of bytes that we actually read. We don't care because we're going to put a string out and whatever got read, and as long as it's not over 100, it's going to be fine. So put s is actually, I haven't shown you put s before, but put s puts a string to the screen. It's like the more convenient version of cout. Actually, we're in C here, so it would be like the more convenient version of printf without having to use the %s to display it. This allows you to put a string directly to the screen. All right. And what are we outputting? We're outputting the buffer. This is the thing we read from the reading the proc mydev. All right. Then we're going to seek to, and I actually want to look up something here. So reposition, read, write, file offset. So this seeks to the beginning of that file. In case we've already been reading from the file and now our point FD no longer points to the beginning of the file, it points somewhere in the middle of the file, end of the file, something like that. So this takes us back to the, wherever we tell it to go back to, which in this case is go back to the beginning. Then we're going to go ahead and write to that file. So we're writing to the same file that we read from. Hopefully that wasn't important, but call it back in a minute. So hopefully we've now reset our position in the file. We could have accomplished the same thing by closing the file and then reopening it. That would have put us back at the beginning of it as well. But this gets us back to the beginning of the file. Then we will write to that file our string. In this case, 33 and 4. This 5 here is the number of bytes we're writing. 1, 2, 3, 4, but where's the 5th byte? Almost. How do you terminate strings? \n kicks it down a line, but in C, the string termination character is \0, right? So we are writing 5 bytes here, and that is this string. Bucket 0, bucket 1, bucket 2, bucket 3, and then bucket 4 is the string termination character. Okay? So that's what we're writing. Then we'll go ahead and go back to the beginning of the file. We'll read from it again. Now, keep in mind that this is a special file. That's why we're doing this lseek stuff. Because when we wrote to it, we didn't really write to the contents of a file. I think you know what I mean when I say file. It's not a normal text file. Instead, we are writing to the computer program that is kind of listening to activity on that file. And so when we write to it, we're writing to that program. When we seek, we're going back to the beginning of that file so that when we read the next time or write the next time, whatever it is, we're calling the program associated with it. Fresh, a new call to it. When we read from the file again, we're going to read into our buffer again, print it out. We should now see that we were able to get our updated IRQ information. So we read it, we changed it, we read it again. All right, and we compile this with our normal GCC user space test. Hello. I'm writing it out. Not. I don't have anything special there. Oh, there we go. Had to run it as super user. Otherwise, I wouldn't have access to the proc file system to open. So we read it in initially. We had our well, 44 and 3, which I think is the state we last left it at when we were directly interfacing with it. Then we changed it to 33 and 4, read it again, and saw that it now has changed. Makes sense? So there's a true to life, use of a user level program talking to the proc file system, communicating with the kernel. All right, questions about that guy? Okay, so that's one example of interprocess communication where we are, the two processes one lives in kernel space and one lives in user space. And we have to use mechanisms for crossing between those two. Now, what if we have two files that live in the same space, whether they're both running in kernel space or they're both running in user space? User space is probably going to be the most obvious for us to mess with. But the idea is that you have two different computer programs that you wrote, and you want these guys to communicate with each other in some way. Okay, so we create our programs, they're running on Linux, they're both in user space, and we somehow want to share information between them. So we need to, if we think about this in real life, we have two people that showed up to the park, and we need to have multiple ways for them to talk to each other at the park. Okay, where we have them caged in so they can only stay in the area of the park, and we're going to just say that, you know, what kind of communication mechanisms might we as human beings provide them? Well, you know, we could shout, right? So I could yell across the park and, you know, say, you know, hey, I'm ready. Or maybe you're playing catch or something like that. All right, another thing you could do is maybe have walkie-talkies, something like that. So some indirect way of communicating. So instead of speaking in a public way where maybe everybody can hear what I'm saying, you know, all bystanders who are there are going to hear me saying I'm ready. Maybe I want to, you know, whisper into the radio and say, hey, you know, I'm ready, whatever it is. And then it's more of a private communication. And we can keep going down examples, right? You know, you can, you know, maybe spray paint something on a big wall that you can see from wherever you are. You come back and check it. You know, maybe we have a, you know, a location that we've agreed upon where I'll leave secrets. What do they call those? Drop locations? Yeah, I mean, that's super sus. I wouldn't, that's the word, right? Sus? Sus. Oh, did I tell you they sent me another trophy? I don't know, the Pro League. What's the name of the game? Among Us. Yeah, Pro Among Us. I got a trophy.
First place to last place.
I hate you. No. That was pretty funny, that when I just popped up at your feet. I didn't know how to use the vents. Like, I'm here. And then I would have killed you, but I didn't know how to. It's like, later. All right. So, yeah, I played Among Us online with a bunch of the students last week, and I was better than everybody. It was the thing. All right, so just like we might have a strategy in real life where we want to make two processes talk to each other, or make two humans talk to each other given some constraints, we have mechanisms inside of our operating systems that provide this for us. And the first one we're going to be looking at here is something called shared files, but we're going to look ahead at the something. Let me just want to bump us ahead here. So homework, research the difference between a pipe and a socket in Linux interprocess communication. Write a 3-page paper comparing these and provide a scenario where each mechanism would be the right tool for the job. All right, so we're going to start off in here, and I'll just spend a couple minutes just kind of preheating it here. But we're going to start talking about shared files at first. And we're not just talking about, we've kind of already talked about plain Jane files at the high level, but what if you kind of want to use a shared file for having two processes communicate? And I mentioned either last class or the class before, we might have to invent a protocol, to kind of, like I used the example with walkie-talkies, right? You say something and you say over, that means the other person's allowed to talk now. You have this like cadence, right? The same thing is true. There's mechanisms within the operating system for working with files that allow us to kind of create a cadence, a protocol for those guys talking. All right, but we're going to look ahead in our homework assignment for where we're going to be going and look at the difference between a pipe and a socket specifically. All right, questions about what I'm asking you to do for homework? All right, so just a quick thing. I mean, you can read through this if you want, but this guy kind of talks about how our process is born, is what we're going to be looking at when we're dealing with all of these inter-process communication things, is the existence of processes and how they start. Well, the obvious way a process starts is when we run it, right? You double click on an icon, you do a /a.out, process starts. Well, as we start getting into inter-process communication, there's going to be other situations in which processes can be born. They can be born as a child process of a running process, and that happens through this fork system call, which you've seen before in on GitHub, where you can fork a repository, which makes a duplicate of a repository. Okay, so it's literally identical to the original, but a forked process knows that it is the clone, because the response, and we'll see this when we get to it, but when you call the fork system command, it returns the process ID. And if the process ID is 0, that means you're the original. The process ID is something other than 0, that means you are the new process that was just born and you have a real process ID on the operating system. You're the child, you're the clone, and you might do something different than the parent is supposed to do. They cloned you for some reason, right? They cloned you for some reason. But the difference here, and we're going to be talking about that, and you've heard this in other classes probably, is the difference between processes and threads. So we'll talk about that some, but that's less important for us here, because when we talk about inter-process communication, it's pretty similar to when we talk about inter-thread communication, where you have multiple threads running in your program and they need to talk with each other for some reason. Maybe you're waiting for 2 threads to finish and this guy has to chill until they're done before he can do the next step, something like that. Like we wrote a multi-threaded merge sort, for example. The final merge can't happen until both the left and right merge sorts finish, that type of thing. So they have to, what's called join. That guy is the inter-process communication tool for doing that. But in any case, we're going to be looking at different examples of inter-process communication over the next several weeks, and that should get us into the midterm-y time period. So we'll go from there. Questions, comments, concerns, bribes?
Is this assignment due for Wednesday then?
Yep. Yeah, very rarely do I give assignments that aren't due the very next class, but
Okay.
But it's a good question, just in case. All right, I'll see everybody on Wednesday.
I have an update on my challenge.
Yeah, I saw you put the thing in chat. You failed already?
No, it doesn't start till this Friday.
I can't run due to my leg. But I'm going to bike for 1 hour every 4 hours for 48 hours straight. Well, what were you supposed to do before? Run for 1 hour?
Essentially, it's running 4 miles, which takes the average person about an hour.
Okay. So you're going to ride the bike for an hour every 4 hours for 48 hours. Oh,
Yeah.
You're like defending yourself by saying it's allowed by the rules?
Yeah, and I linked it. So
I see. Proof. But does it say an hour, or does it say you can ride the bike for 4 miles? I
It
don't
says
have to go read it. What does it actually
it's
say?
45 minutes to an hour, so I picked the hardest option, an hour.
Okay. But I think we can both agree you're still gonna fail at this challenge.
I'm not going to.
Oh, you will. I have no faith in
Oh, thanks.
you.